Welcome, everyone. For today's prep, we're going to look at how to integrate partial fractions. So we've seen how to take a rational function, break it apart into a whole bunch of little fractions called partial fractions. And now we're going to see, well, how do we take each of those little fractions and integrate it? And it really comes down to kind of four special cases. So I have them listed here. Talk a little bit about each of these. So the first two that we see here, we have the fraction 1 over kx plus d, and then we have the fraction 1 over kx plus d raised to the power n. So these are partial fractions when we have a linear term. So the first fraction, this is when we have a linear term of multiplicity 1, and we would see something like this if we have a linear term with a multiplicity greater than 1. So again, this is a constant k, just some constant, just some number, and then d is also a constant here. And how you could prove each of these two formula is with a u substitution. So let's look at the first one. We could let u equal the term that's in the denominator, so kx plus d. So we're just letting our u equal this. And then if we were to calculate du in this case, derivative of kx plus d would be k, and then we multiply by dx. And if we look at our integral, we only have a dx there. So we would have to solve this equation for k. So we divide both sides by k. And we get dx is equal to 1 over k times du. And now you can kind of see where the pieces are going to come from. So our integral is ultimately going to involve 1 over u. The antiderivative of 1 over u is natural log. And then we replace our u value with what it was, so kx plus d. So that's how we get this natural log absolute value kx plus d. And then you can see from our work with our differential where that 1 over k is. So we end up with a 1 over k out in front. So this is really just a special k form for this natural log antiderivative. So we integrate the fraction. We end up with natural log of the term that's in the denominator. And then we take the constant k that's in front of the x, and we flip it, put it in front. And this formula only works, any of these formula, only work if it looks exactly like this. So if this had a higher power on the x, that formula doesn't work. So it's got to be just a linear term, a constant k times x plus some other constant d. Now we could do the same thing for the next one where we have 1 over the kx plus d, but now there's an exponent around this whole thing. So it's still a u substitution. So you'd still let, in this case, u equal the kx plus d. And then you do your power rule. So you could write this as kx plus d raised to the negative 1 if you wanted to. Or negative n, rather. So you just make the exponent negative. And then you do regular power rule. So you keep what's inside the parentheses the same. You add 1 to the exponent. You take that new exponent, flip it, put it in front. And then again, because we're doing a u sub, and this is our u substitution, we're going to end up with that 1 over k that goes in front. So this is just another special k-form antiderivative. Now for the last two here, these show up when we're trying to integrate an irreducible quadratic. So we have two cases. One case when we have an x on the top and then x squared plus a squared in the denominator. And in this case, this integrates to 1/2 times the natural log of the term that's in the denominator, x squared plus a squared. And again, this one you could prove it with a u substitution. So you could let u equal the x squared plus a squared. And then if you calculate the differential, you get 2x dx. And if you kind of start to think about how things are going to match up, well, the x squared plus a squared, that's going to become our u. And then we have an x up here and a dx. So the only thing that we don't have is that 2. So we would have to divide the 2, get it over to the other side, and that's where the 1/2 is coming from. So when it's x over x squared plus a squared, we get to use a u substitution, and it's 1/2 times that natural log. Now, if we have the same type of irreducible quadratic, x squared plus a squared in the denominator, but just a constant in the numerator, so not an x, well, then this integrates very differently. And the antiderivative of something like this involves arctan, or inverse tan. So this is inverse tan of x over a, and then with a 1 over a in front. So basically, the way you can figure out the a value here is whatever number you have in your denominator that's part of this specific form of this irreducible quadratic, you just do the square root of it. So a is equal to the square root of a squared, and that's what you're going to fill in. All right, so let's try a few examples. So let's look at examples 1 and 2. Now, these were both rational functions that we've already found their partial fraction decomposition of. We did these in class and in the last prep video. So for the first one, this rational function, 2x plus 5 over x minus 1 times 3x plus 4, we did the partial fraction decomposition for this. So when we're presented with a problem like this, where we have a rational function, we're trying to integrate it, it doesn't hurt. Go off to, leave a little space, go down a few lines, and work out the partial fraction decomposition. And what we found is that this fraction became 1 over x minus 1 minus 1 over 3x plus 4. So this was the partial fraction decomposition. So this was our decomposition here. We broke that rational function apart. This didn't involve any integrating. This was just purely algebra. But now, once we get it to this point, each of these individual fractions is something we can integrate. So that first one, let's look at the 1 over x minus 1. So this is a linear term, and there's no visible exponent on this. So this is, well, actually both of these are the first case here, this 1 over kx plus d. So our antiderivative of this first fraction is going to be the natural log of absolute value x minus 1. And then we take the constant that's in front of the x, which in this case is just 1, and we flip it and put it in front. So 1 over 1, which we won't write. Now for our second fraction, the 1 over 3x plus 4, again, same kind of deal. This is a linear term, 3x plus 4, and this is just that 1 over kx plus d form. So this is our special k form here. So when we integrate, the minus sign will stay where it is. We'll get the natural log of the absolute value of 3x plus 4. But now we take that constant that's in front of the x, in this case 3, and we flip it and put it in front of the natural log. And then we've done our constant, or we've done our integrating, so plus c at the end. And that's it. That's it. So the integration part for these is normally the easy part. Well, easier part. Normally most of the work is doing all that algebra to break the rational function apart. So there was a lot of work here that's kind of hidden behind the scenes. We did that last time. Let's try example 2. So integral of 1 over x squared minus 25, first step when we have a rational function like this would be to do the decomposition. And notice that this is a different format. It looks very similar. If we pop back up to our, it looks very similar, 1 over x squared with a constant squared. The difference here is this one has a plus. So this is an irreducible quadratic when we have that plus sign in between those two squareds. And in the case of example 2, this actually did factor down into just two different linear terms. So when we did our partial fractions in this case, what we found is that this rational function became 1 over 10 divided by x minus 5 minus 1 over 10 divided by x plus 5. So I make sure I got the right coefficients in the right spot there. So again, there's a lot of work hidden here behind the scenes. We did this in class. So we did the decomposition for this. So that's where most of the work happens. And then once we get our partial fractions all split apart like this, then we just integrate. And in this case, the 1 over 10 is a constant multiple. So we can just put that in front. And then we're really just integrating 1 over x minus 5 there. So again, that's one of our 1 over kx plus d's. So it's going to be the natural log of the absolute value of x minus 5. And then we take the constant that's in front of the x and we flip it and put it right in front of the natural log there. And in this case, it's just 1 over 1, so 1. We don't write that. So the antiderivative of this first term will be 1 over 10 times the natural log of absolute value x minus 5. So that's the first fraction. And then if we integrate the second fraction, same kind of deal here. So again, we have subtraction in the middle, so we'll keep that where it is. The 1 over 10 on top is just a constant multiple, so we'll just kind of throw that out in front. And we really just want to think about what is the antiderivative of 1 over x plus 5. Well, again, that's just one of our special forms. So it's natural log absolute value x plus 5. And then leave a little space here just in case. But then the constant in front of the x is just a 1. So again, if we flip it, we end up with 1 over 1, which is just 1. So we won't write that. And there's our antiderivative. And now that we're done getting the antiderivative, we throw on our plus c at the end. All right, so these partial fractions really allow us, really make it nice to finish off the integration. Let's try one more, the example 3. So this is also one we did in class. So we had this rational function 2x squared minus x plus 4 over x cubed plus 4x. And what we saw with this one is when we factored it, the denominator had an irreducible quadratic. And we went through and did the decomposition. And what we found is that this function breaks apart into, well, we ended up with one linear term, which gave us, and we figured out the coefficient was 1 over x. And then we had one quadratic term, which gave us the fraction x minus 1 over x squared plus 4. So that was our decomposition that we did. Again, there was a lot of work that's hidden behind the scenes here. So when you're doing these integral problems, the way you kind of want to set it up is maybe down here, work on doing the decomposition, show all your work for the decomposition, and then once you get the result, bring that back up to the main line of your work, and then the integration is normally pretty quick. All right, so this is different though than the ones we've seen. So this irreducible quadratic, we want to break this up into two separate fractions based on these terms in the numerator. So that's our strategy here. We're going to first rewrite this just a little bit further. So we're going to have the 1 over x, That's fine. We can deal with that. But then we're going to make that x that's in the numerator, it's going to get its own fraction. So we'll have plus x over x squared plus 4. And then the negative 1 in the numerator there is also going to get its own fraction. So we'll have negative 1 over x squared plus 4. And how we integrate each of these is, well, a bit different. So first, the 1 over x, that's something we can just do. So that's natural log absolute value x. That's just one of our basic antiderivatives. Now, what about this x over x squared plus 4? Let's go back up to our list. So when we did our integral list here, we had two integral rules for irreducible quadratics. One of them had an x in the top, one of them had a 1 in the top of our fraction. So we want to look at this one, x over x squared plus a squared. So the way this one works, natural log of the denominator, and then with a 1/2 in front. So that's the situation we're running into right here. So it's going to be the natural log of the denominator. Now, technically, this is an irreducible quadratic, and all the terms here are positive, so we don't really need the absolute value sign here. And then we have a 1/2 in front. And then we got to get the antiderivative for the next term, the 1 over x squared plus 4. But now this one's going to integrate differently. So let's pop back up. And for 1 over the x squared plus 4, when we have that irreducible quadratic and it's a 1 in the numerator, or a constant, it involves this arctan function. So it's inverse tan of x over a with a 1 over a in front. And again, the way you can figure out this a value is you take whatever number you have and you do the square root of it. So if we're looking here, the a value is going to be the square root of 4, which is 2. So when we do our antiderivative, it's going to be the inverse tan of x over 2, and then we end up with a 1 over 2 in front. And then plus c. All right, so that's going to do it for today. We'll finish up a couple examples in class. But it really comes down to just having these specific formulas at least memorized, or, at least understand where to go to kind of quickly look them up. But you can do most of these with a U substitution. Really, the only one that requires kind of some memorization is probably this one right here. All right, so we'll practice a little more in class. So we'll see you then. Bye-bye.